Okay, hello everyone, in a new video in part 3 of chapter 10, which is the chapter of Archimedes upthrust in the third unit of mechanics. Then we are still solving exercises on what we have explained in part 1, and we have reached exercise number 5. The aim of this exercise is to determine experimentally the volume of the cavity of an iron sphere S. Okay, before I start solving this exercise, let me explain what is meant by cavity. Okay, cavity of an iron sphere S. So let's suppose that this is the sphere S that has the shape of a sphere, and this sphere is made up of iron. Then the aim of this exercise is to determine whether this sphere S has a cavity or no. So if it doesn't have, if this solid S has no cavity, then it will be completely made up of iron. So it is completely an iron bone, iron sphere. However, if it's made up of cavity, so part of it is made up of iron. Let's suppose that this is the part made up of iron. So the shaded part is completely made up of iron, and the cavity is at the center of the sphere. This is the cavity. And here by cavity, it is meant an empty space inside the sphere. So in this case, this empty space is at the center of the sphere. So looking at the sphere from outside, one cannot distinguish whether this sphere is completely made up of iron or no. In other words, whether it has a cavity or no. And the aim of this exercise is to determine whether this iron sphere has a cavity or no. So let's check out. Given that G is equal to 10 newtons per kilogram, which means that we are performing this experiment on Earth, on the surface of Earth. Then number 1, first experiment. We attach S to a dynamometer. So here by dynamometer they mean spring balance, and we know that the spring balance measures the weight. The dynamometer indicates 7.80 newtons at equilibrium. Okay, here because they didn't mention any liquid, so we suppose that the solid S being attached to the spring balance in air. So 1.1. Name the two forces acting on S. For sure, because the solid S is made up of iron, so it has a mass, then it will be directly subjected to the weight. And we have G. So the first force is the weight W. And because we have a spring balance, we have a spring, then it will be directly subjected to the tension T in the spring. And these are the two forces acting on S. Now 1.2. Okay, here, what does this weight represent? We always have two weights, the real weight and the apparent weight. Here, because we are performing this experiment in air. Why in air? Although they didn't mention we are performing this experiment in air, but simply because we don't have any liquid. So in this case, this weight represents the real weight, which is the indication of the spring balance given by 7.80 newtons. Give the relation between the value of these forces. And here, by the relation between these forces, they mean the vectorial relation or the vector relation, which holds at equilibrium. Then let's write as a title at equilibrium. Then how do we apply this condition? Always on the left we write the sum of forces acting on the solid S, and they are given by the weight W and the tension T. Then weight vector plus tension vector is equal to 2. And on the other side, on the right hand side, we'll write the zero vector corresponding for the condition of equilibrium, and we don't forget the vector over the zero. Then moving T to the right hand side, we have that W vector is equal to minus T vector. So what does the first equation means? That the effect of the forces cancel each other, which gives us the zero vector corresponding for the equilibrium, whereas the second equation tells us that both forces have the same line of action, the minus sign for the opposite direction, and same magnitude. And in the same part they are telling me deduce the mass of S. And here by deduce, it means that we need to use the previous part. So in the previous part, we determine the condition of equilibrium, which is given by W vector is equal to minus T vector, and we need to deduce the mass from this condition, knowing that the dynamometer indicates 7.80 newtons at equilibrium, which is the tension and the weight. So here we have that the weight and the mass are related via the following formula, and we are interested in determining the value of M. So constructing the triangle of this formula, here because we have multiply, then W will be at the top, M and G at the bottom. We are interested in calculating the value of M, which is given by W divided by G. So here, the dynamometer indicates 7.80 newtons, which is the value of the weight and the tension at the same time. Then 7.8 divided by 10. This is what is meant by deduce. So plugging this fraction on the calculator, it will give us 0.78. Since both W and G are in the SI, so the value of M is in the SI, which is kilograms. Then the mass of this sphere is given by 0.78 kilograms. So now we have that the value M is given by 0.78 kilograms. Now in 1.3, calculate the volume V1 of iron given the density of iron is equal to 7,800 kilogram per meter cube. So we have the density and we have the mass. One can calculate the volume V1 of iron using the following formula, that the density is equal to mass over volume, knowing that we are interested in determining the volume. So constructing the triangle of this formula, here because we have divide, then rho will be at the bottom, M at the top, V here, and we are interested in determining the value of V, which is denoted by V1. So putting our hand over V, V is given by M divided by rho. Now the value of M is given by 0.78. And the value of rho is given by 7,800. Plugging this on the calculator, it will give us 1 times 10 to the power minus 4. Since everything in the SI, M and rho, then the value of V1 will be in the SI, which is meter cube. So the volume V1 is given by 1 times 10 to the power minus 4 meter cube. And let me write here that V1 is equal to 1 times 10 to the power minus 4 meter cube. Let me make some space. Now number 2, second experiment. Before we continue, let me explain what does this V1, the volume V1, represent. Notice that we calculated this volume using the formula density is equal to mass over volume. So this V1 is coming from this formula using density is equal to mass over volume. So what does this volume represent? It represents the volume corresponding for the material of density rho and for the mass m. So this density, we have used the density of iron. So this volume represents the volume of real iron inside the sphere. Okay, now the sphere S is still attached to the same dynamometer, is completely immersed in water. So here this is important, it's completely immersed in water. The dynamometer indicates 6.3 newtons. Now 2.1, what is the value of the parent weight of S? Now, so always the dynamometer or the spring balance measures weight. So it will either measure the real weight or the apparent weight. Here, because it's completely or immersed in water, then it will measure the apparent weight. For sure it is at equilibrium. Then let's say since the suspended object, which is given by us, is immersed in water or in liquid. In this case the liquid is water, is immersed in a liquid. At equilibrium, then the spring balance or the dynamometer, let's say, is the same. Indicates its apparent weight. Then in this case the apparent weight is given by 6.3 newtons. So let me write here that the apparent weight is given by 6.3 newtons and the real weight, let's say WR, is given by 7.80 newtons. And in the same part they are telling me deduce the value of F of Archimedes upthrust exerted by water on S, and by deduce it means that we need to use the part just previously before. Then we have the value of the apparent weight and we have the value of the real weight. We can determine the value of F using its definition, real weight minus apparent weight. The value of the real weight is given by 7.8, the value of the apparent weight is given by 6.3. Now plugging this on the calculator, it will give us 1.5. Since both the apparent weight and the real weight are expressed in newtons, so the value of F will be expressed in newtons, which is the SI. Then the value of the Archimedes upthrust exerted by water on S is given by F is equal to 1.5 newtons. Now in 2.2, determine the volume V2 of the sphere S, given the density of water is equal to 1000 kg per meter cube. So let's determine this volume. Now we know that the volume and the value of F are related via the following formula, that F upthrust is equal to the density of the liquid times Vi times G, knowing that we are interested in determining the value of Vi. Now constructing the triangle of this formula, here because we have multiplied and F upthrust will be at the top, rho L, Vi and G at the bottom. So putting our hand over Vi is given by the value of F upthrust, which is denoted by F, divided by the density of the liquid, which is given by water. Let's denote it by rho L multiplied by G, which is given to be 10 newtons per kilogram. Now 1.5 divided by the density of this liquid, which is water, 1000 in the SI, multiplied by 10 the value of G. Plugging this fraction on the calculator, it will give us 1.5 times 10 to the power minus 4 meter cube. So the volume Vi is given by 1.5 times 10 to the power minus 4 meter cube. But notice that this volume represents the immersed volume of the solid S. They are asking me to determine the volume V2 of the sphere S. Yet we didn't answer the question, but here because the solid S is completely immersed in water, we can say that since S is completely immersed in water or in this liquid, then we have that the volume of the immersed part is equal to the volume which is denoted by V2. 1.5 times 10 to the power minus 4 meter cube. So V2 is equal to 1.5 times 10 to the power minus 4 meter cube. So now here we have two volumes. The volume V1 of iron, so V1 stands for iron. Here they are telling me calculate the volume V1 of iron, and the volume V2 of the sphere, which is given by 1.5 times 10 to the power minus 4 meter cube. So now before we get to the third part of this exercise, let me explain the difference between these two volumes. So here, suppose we have this solid, the same solid, which has the shape of the sphere. Now we have two volumes, V1, which is given by 1 times 10 to the power minus 4 meter cube, which represents the amount of iron, the quantity of iron, and V2, which is given by 1.5 times 10 to the power minus 4 meter cube, which represents the volume of the sphere. So this volume V2 represents the volume of the sphere, which is actually the volume which this sphere takes. Whereas this volume V1, so this is the volume V2. This is the volume V2, the outer volume. Whereas the volume V1 is equal to 1 times 10 to the power minus 4 meter cube represents the amount of iron, or the volume, the real volume of iron found in this solid. Okay. Now in 3.1, by comparing V1 and V2, verify that the sphere is S is hollow. And hollow, it means that there is a cavity. So, or made up of cavity. Made up of a cavity. And by cavity, it means that it has an empty space. Now notice that V1 is given by this and V2 is given by 1.5 times 10 to the power minus 4 meter cube. So let's compare them first. We know that V1 is given by 1 times 10 to the power minus 4 meter cube, whereas V2 is equal to 1.5 times 10 to the power minus 4 meter cube. So here in this case, V2 is greater than V1. So what do we deduce? We deduce that the volume V2 corresponding for the sphere is greater than the volume V1, which represents the iron, and this difference is due to the cavity found inside the sphere. So suppose that this is the sphere S, and this is the cavity. So this is the volume V of iron, V1 of iron. So what does V2 represent? V2 represent this total volume of the sphere S. For this reason, V2 will be greater than V1 due to the cavity present inside the sphere S. So verify that the sphere S is hollow. Then let's say since the volume of the sphere is not equal, or let's say is greater than the volume of iron, then the sphere S has a cavity. Now in 3.2, calculate the volume V of the cavity, and the volume V of the cavity is due to the difference between the two volumes V1, V2 for sure, the greater minus, so the greater here by, I mean V2, which has a greater value and given by 1.5 times 10 to the power minus 4. So by definition, the volume of the cavity is given by the volume V2 of the sphere minus V1. So this is the difference, which is the cavity. Then 1.5 times 10 to the power minus 4 minus 1 times 10 to the power minus 4, which is given by 0.5 times 10 to the power minus 4 meter cube. Then the volume of the cavity is given by 0.5 times 10 to the power minus 4 meter cube. And now let's move to the next exercise, which is exercise number 6. In order to determine the density rho of a small metallic block taken from the ground, we consider a spring balance having its upper end fixed to a support and a water container. Take a G is equal to 10 newtons per kilogram, which means that we are performing this experiment on Earth. And the density of water, so rho W is for water, because here rho is for the small metallic block, is given by 1000 kilogram per meter cube. Number 1, in the first experiment, we suspend the block from the free end of spring balance. The system spring balance block is at equilibrium in air. This is important. The spring balance indicates 5 newtons. Deduce from this indication the magnitude of the weight of the block and its mass. So first, let's start by the weight. So always the spring balance indicates weight. And by weight, we either mean the real weight or the apparent weight, because it's being performed at equilibrium in Earth and the spring balance indicates its real weight. Then let's justify, since the suspended object, here they are not naming it to be S, but it's okay. The suspended object is in air at equilibrium, Then the spring balance indicates its real weight, which is given by the real weight is equal to 5 newtons. And here by the real weight, it means that the weight which is given by m times g. In the same part, they are telling me to deduce its mass. We know that the real weight and the mass are related via the following formula, knowing that we are interested in determining the value of m. So constructing the triangle of this formula, here because we have multiplied and w will be at the top, m and g at the bottom, putting our hand over m, then m will be given by w divided by g, then 5 divided by 10. This fraction is given by 0.5 because w and g are in the SI, so the value of m in the SI is given by kilograms. Then the mass of this solid is given by 0.5 kilogram, which is the metallic block. Now in number 2, in a second experiment, the block being still suspended from the free end of the spring balance is completely immersed in the water container. At equilibrium, the indication of the spring balance becomes 3 newtons. This difference indication of the spring balance is due to Archimedes upthrust F vector exerted by water on the block. So here we can directly guess that this solid S it will be subjected to Archimedes upthrust F because we have liquid, and whenever we have liquid, the solid S will be directly subjected to F upthrust exerted by water on the block. Now 2.1, specify the line of action and the direction of F. We know that always the line of action and the direction of F is vertically upward, and the line of action is vertical. And the direction is given by upward. Now in 2.2 we need to determine the magnitude f of f, and we can determine the magnitude f of f using its definition. F is equal to the difference between the real weight and the apparent weight. We already know the value of the real weight, which is given by 5 newtons. It's left to determine the apparent weight, and this can be done or can be determined using this given. Here they are telling me that the indication of the spring balance becomes 3 newtons. Always the spring balance measures weight, so it will be either the real weight or the apparent weight. Because the solid S being immersed in water at equilibrium, so this indication represents the apparent weight. Then first, it's more convenient to justify that how or what's the value of the apparent weight. Then let's say since the suspended object is immersed in liquid, at equilibrium, then the spring balance indicates its apparent weight. Then in this case the apparent weight is given by 3 newtons. And now we know the value of the apparent weight and the real weight. The magnitude f of f vector can be determined from its definition. F is equal to the real weight minus apparent weight, then 5 minus 3 is given by 2. Since both real weight and apparent weight are expressed in newtons, so the value of f will be expressed in newtons. So the value f, the magnitude f of f upthrust vector exerted by water on this metallic block is given by 2 newtons. Then F is equal to 2 newtons. Now in 2.3, calculate the volume V of the block. And we know that the volume and the value of F are related via the following formula, that F upthrust is equal to the density of the liquid times the volume of the immersed part times G. Then let's determine the value of Vi. Now constructing the triangle of this formula, here because we have multiplied and F upthrust will be at the top, rho L, Vi and G at the bottom, we are interested in determining the value of Vi. Putting our hand over Vi, Vi is given by the value of F upthrust, which is denoted by F, divided by the density of the liquid, which is denoted by rho W, corresponding for water, multiplied by G. Now the value of F is given by 2, the value of rho is given by 1000, and the value of G is given by 10. So plugging this complicated fraction on the calculator, then the value of Vi is given by 2 times 10 to the power minus 4. Since everything in the SI, so Vi will be given in the SI, which is meter cube. Then the volume of the immersed part is given by 2 times 10 to the power minus 4 meter cube. And this is important, that this volume represents the volume of the immersed part. So we didn't answer the question because they are telling me to determine the volume V of the block. Knowing that this is completely immersed in water, then in this case here we have that Vi is equal to V. Then let's say since the solid, which is the metallic block, is completely immersed in a liquid, then V is equal to Vi is equal to 2 times 10 to the power minus 4 meter cube. Then the volume of this metallic block is given by 2 times 10 to the power minus 4 meter cube. Now number 3, deduce from the above two experiments the density rho of the block. And from these two experiments we have, so let me write here that the volume of the block is given by 2 times 10 to the power minus 4 meter cube. So what we have determined in these two experiments is that from the first experiment we have determined the mass, and from the second experiment we have determined the volume V of the block. Now we can calculate the density or deduce the density using its formula. Density is equal to mass divided by volume. The mass is given by 0.5 and the volume is given by 2 times 10 to the power minus 4. Plugging this fraction on the calculator, it will give us 2500. Since everything in the SI, so the unit of rho will be in the SI, which is the same of water, which is given by kilogram per meter cube. Then the density rho is given by 2500 kilogram per meter cube. Now let's move to the final exercise for this part, which is exercise number 7. The aim of this exercise is to measure the density rho of liquid L. So here we need to measure the density rho of liquid L, not for the solid. For this purpose we have a solid S whose weight is of magnitude W is equal to 5 newtons. So what does this weight represent? It represents the real weight. A spring balance and a graduated cylinder containing liquid L of volume V1 is equal to 250 milliliters. So this quantity of or volume of water is given by V1 is equal to 250 milliliters. Why this represent the real weight? Because they didn't mention any liquid, and in particular here if we look at this document 1, we can see when the solid S is attached to the free end of the spring balance, and here the spring balance indicate 5 newtons, yet they didn't mention document 1. Here they mentioned document 1, below document 1. Now we suspend S from the spring balance and immerse it completely in a liquid L, At equilibrium, the level of the liquid corresponds to the graduation V2 is equal to 300 milliliters, and the spring balance indicates 4.6 newtons as shown in the document below document 2. So they mentioned document 2, now we can use it. So when the solid S is immersed in the liquid, here it's completely immersed as we can see. Okay, immerse it completely in a liquid L. So the level of water rises from 250 milliliters to 300 milliliters. So the volume of this liquid now is given by 300 milliliters because the solid S occupies some space in this liquid. At equilibrium, the spring balance indicate 4.6 newtons as shown in this document. So the indication of the spring document 1 is given by 5 newtons, and here the scale is given for sure multiplied by 1. Here it's given by 4.6 newtons. So here the spring balance measures the weight. Here, because we have a liquid, then this weight will be given by the apparent weight. Now in number 1, they are telling me indicate the line of action and the direction of F. Take G is equal to 10 newtons per kilogram. The solid S is subjected to the Archimedes upthrust force F vector of magnitude of F. So this represents the Archimedes upthrust. Number 1, indicate the line of action and the direction of F. We always know that F acts on a solid immersed in it always vertically upward. Then the line of action is given by vertical, and the direction is upward. Now in number 2, let W apparent be a vector be the apparent weight of S of magnitude W apparent. Write the expression of F in terms of W and W apparent. So they are asking me about the definition of F. What does W represent? The real weight, and this is the apparent weight. We know that the magnitude of F is given by the real weight minus the apparent weight. Here the real weight is denoted by just W, no subscript. Now in number 3, calculate F. We know that the value of W is given by 5 newtons. Let's justify the value of W apparent. Let's say since the solid S, or the suspended object, is immersed in a liquid, then the spring balance indicate its apparent weight. So the value of the apparent weight is given by, in this case, 4.6 newtons. Then the value of F can be determined using W minus W apparent, which is 5 minus 4.6, which is given by 0.4. Since both are expressed in newtons, so the value of F is in newtons. Then F is equal to 0.4 newtons. We are done with part 3. Now number 4, so here let me write that F, the value of F upthrust is given by 0.4 newtons. Now in number 4, calculate in milliliter, then convert it to meter cube the volume V of the displaced liquid. So here we need to determine the value V of the displaced liquid, knowing that we have V1 is equal to 250 milliliters and V2 is equal to 300 milliliters. What does the displaced liquid represent? It's the difference between this liquid and this liquid. So V is given by V2 minus V1. They are telling me to calculate in milliliters, so they require that the unit of V first must be in milliliters, so V2 must be in milliliters as well as V1. Then we will convert milliliters to meter cube. Then 300 minus 250 is given by 50 milliliters, since both V2 and V1 are in milliliters, so the volume V of the displaced liquid is given by 50 milliliters. Now V, which is given by 50 milliliters, in order to convert from milliliters to meter cube, we simply multiply by 10 to the power minus 6. Then 50 times 10 to the power minus 6 is given by 5 times 10 to the power minus 5 meter cube. Then the volume V of the displaced liquid is given by 5 times 10 to the power minus 5 meter cube. Now in number 5, determine the density ρ of the liquid in kilogram per meter cube. Determine the density ρ of the liquid L in kilogram per meter cube, okay, in the SI. So the first thing that comes to our mind is that density can be calculated using mass over volume. Here we should be very careful, and this is tricky. We are determining the density of the liquid. And we know that whenever we use a triplet formula in physics made up of a triplet, which means 3 quantities, these 3 quantities must be related to the same object. For example, when we're applying Ohm's law to a resistor, we say that U is equal to Ri. If we need to determine the resistance, which is given by U divided by I, this voltage must be the applied voltage across this resistor, which is UAB, and I must be the traverse current across this resistor and not any other resistor, because we know that across an electric circuit we may have several resistors, and here the same applies. We need to determine the density of the liquid, so this mass must be the mass of the liquid and the volume V of the liquid. So we already know that the volume of the displaced liquid is given by 50 milliliters that we have already calculated, but we don't know the mass of this liquid. One cannot say that the mass of this liquid is given by, for example, M is equal to W divided by G, which is 5 divided by 10, which is 0.5 kilogram. This is wrong. Why it is wrong? Because this mass represents the mass of the solid S and not for this displaced liquid. Okay, so we cannot use this formula in order to determine the density of this liquid. And we know that the density of the liquid and the value of F are related via the following formula, that F upthrust is equal to the density of the liquid times VI times G. And we are interested in determining the value of ρL, which is the density of the liquid. Now constructing the triangle of this formula, here because we have multiplied that F upthrust will be at the top, ρL, VI and G at the bottom, then the value of ρL, which is denoted by ρ, is given by the value of F, which is F upthrust, which is denoted by F, divided by the immersed volume, which is V, and multiplied by G. Here no need to mention that the solid S is completely immersed in liquid, so VI is equal to V, because this VI represents the volume of the immersed part, which is the same as the volume of the displaced liquid. Now the value of F is given by 0.4. The value of V is given by 5 times 10 to the power minus 5, which we have determined here in the SI, because ρ must be in the SI, which is kilogram per meter cube, and the value of G is given by 10. Plugging this fraction on the calculator, it will give us 800. Let me write it here. Since everything in the SI, so the value of ρ will be in the SI, which is kilograms per meter cube. Then the value ρ is given by 800 kilogram per meter cube. And by this we have finished solving this exercise. And that's it for me in this video, guys. In the next part we'll complete the explanation of this chapter.